We're introducing the chain rule in this video. We need to recall what composition of functions means, or the function of a function. So composition of functions is where we use the chain rule when we find the derivative. So composition of functions, which essentially means a function of a function. Of a function perhaps too. It doesn't just have to stop as one function of another function, it can go further. But for example, if we had, let's say we throw a pebble into a pond, okay, and the way it generates the waves coming out as such, we might have a formula which relates the radius of each of the waves in accordance to time. And let's pretend that that's r equals 2t. So we have a function of r and t. But let's say too the area of these waves, alright, which is given as a is pi r squared. So that's actually a of r. Can we write an a of t? So how does the area become affected by changing time? Well, we can, because we can put this function inside that function. So a is pi r squared, which is pi times r squared, which is 2t all squared, which is pi times 4 times t squared, or 4 pi t squared. So hopefully that's not a new idea, because if you're going to use the chain rule for differentiation, you need to recall this idea of composition of functions. How do we find the derivative of things in this sort of situation where we have a function of a function? So starting with Leibniz notation, it can be shown with limits, like we sort of did in the previous videos, partially done. We can show that the derivative of a function dy dx is dy du times du dx. Now that's a times there, it's not always written. What does this mean? It means that y is a function of u. It also means that we have u as a function of x. So can you see now the link between that and the composition of functions? Even though we've used different symbols for our variables, that doesn't matter. So if we needed to find the derivative of y in regards to x, we need to find two things. We need to find dy du, which is the derivative of y with respect to u, so it'll be the derivative of that function. And we need to also find du dx, which would be the derivative of that function with regard to x. So the first one, we need to find the derivative of y in regards to u, and second one, we need to find the derivative of x in regards, u in regards to x. So that's essentially the chain rule there in Leibniz notation. We can also write it in the other notations. So the compressed or abbreviated function notation, we can't really get away without writing the independent variables in brackets. Okay, you could with the product and quotient rule, but yeah, with composition of functions, we need to be clear about what we're differentiating in regards to. So y dash of x equals y dash of u times u dash of x. Can you see the link with what's written above? Hopefully you can. There and there, color coordinated. That's no accident. Okay, they're coordinated. And the full function notation, we just scroll down a bit first. The full function notation with the operator notation there, d dx. So we have the derivative, now be careful here, f of g of x, so it's a function of a function. Okay, sometimes I'll call that inner function and outer function. The derivative of that is f dash of g of x times g dash of x. Okay, so we can see the derivative of the inner function and the derivative of the outer function. I don't know if that's the actual correct way of describing an inner and outer, but that's how I often describe it. It seems to make sense to people. Okay, so you can see that they correspond. So again, just like with the product and quotient rule, you need to be aware of the different notations, and they're three of the most common ones. So how do we do this? Well, firstly we need to identify when we have a function of a function. We need to use the chain rule, because sometimes tasks don't tell us that. We need to recognize it. This one here, the derivative with regard to t of 3 outside of 4t plus 7 to the 6 is indeed one of those. And what we do, we don't have all these letters that you saw when we wrote the rule down. Okay, so we need to supply them, and I'm going to use this first notation here for this particular example. Okay, and it doesn't matter which notation really, but I'm going to use the first one. So y would be the entire function, because I didn't call it that when I presented the question, so I've got to give it a name. So the whole thing's y. So we've got to find dy dt. That's just paraphrasing the question, okay? So dy dt, have you noticed the little, this is no accident. Have a look. Dy dx, dy dx, top and bottom, du. Alright, so that's actually right, and even though they're not strictly fractions, it's like you could almost cancel those out and you'd get dy dx. It's a bit of a pattern. Always look for patterns. So applying that pattern here, we would have dy and dt like that. And, well, we don't have a u. We need another letter, don't we? Well, that's important. Have a look at the inner function. Look for an inner function. Now, there is a function in its own right inside here. So it is a function of a function. The inner function is 4t plus 7. Now, I'm going to let that equal to u. Okay, it doesn't matter what letter of the alphabet. U's commonly used one. Let u equal 4t plus 7. Now, the derivative of, oops, that should be a u. Derivative of u with regards to t is easy to find. It's 4. So if du dt equals 4, and that's actually good news, because that will help us complete the pattern if we can get du dt there, and we'd also need a u there. So do we have something that relates y and u together? Well, we do. Once we've made this substitution here, we now can rewrite y again, y. So y equals 3 times, we've made the substitution above, so instead of 4t take 7, we're writing u to the 6. So if we're writing dy du, so the derivative of y with respect to u, it's 18 u to the 5. So let's put these in. So we need dy du first, which is 18 u to the power 5, times du dt. So there's du dt there, times 4. Okay, so 18 times 2 is 36, and 72 u to the fifth. Now we need to unsubstitute because we want dy dt. We've almost got it. We've just got to go back and unsubstitute so we've got something in regards to t. So it'd be 72 outside of 4t plus 7 to the power 5. There's our derivative. It's interesting what we can do with the chain rule. In the previous video you might remember we used the quotient rule to find the derivative of this here. We can also use the chain rule, which arguably is easier. Some people may prefer it. Sorry, that should be a t. So to find dy dt, I'm going to find dy du dt using the same notation, and we need to make u equal to something here. Now that's a bit strange if we look at it like this, but can we rewrite the function as 3t take 4 times 2t plus 5 to the negative 1, because 2t plus 5 on the denominator can be written as a product raised to the negative 1. So then we've got a product rule and we've also got a chain rule as well. So that makes it a little bit higher level. But you can use the chain rule there. Okay, so that part of it will be done with the chain rule. And then when that's done, you've found the derivative of that, then you can use the product rule to do the whole thing. To save time on the video, I'm not going to go ahead and do that, but sometimes you'll see ones like that done.